Question 14 is some geometry. In this question, we're asked how many angles, where the angle is strictly greater than 0, but less than or equal to 2 pi. If you're not comfortable with your angle being measured in radians, you can convert these to degrees by remembering that pi radians is the same as 180 degrees. So really what's going on is our angle theta here has to be strictly greater than 0, but less than or equal to 360 degrees. Anyways, how many angles between 0 and 360 degrees will a rotation counterclockwise about the origin, the point 0, 0, map the octagon in this figure onto itself? This is probably a problem you can just kind of look at and talk yourself into the right answer. But in case you can't, let me try to talk you through a method that'll work. And maybe by coming up with a more concrete method, you'll have the tools to solve similar problems which aren't maybe quite as apparent. When you're rotating around the origin, all of the points will travel along a circle centered at the origin. So if I consider this point up here at 0, 4, here's the best circle I can draw. If I rotate this figure, 45 degrees counterclockwise, this point that started out at 4 is going to travel 45 degrees along this circle and end up right here. I'll change the color a little bit to make it easier to see. The important fact is that this new point is not on the original octagon. Nor would this point end up on the octagon if I rotated any angle between 0 and 45 degrees. So like 20 degrees or so would leave me right here, and 30 would be somewhere in here. In fact, there's only one other point on this octagon that falls on this green circle, and that's this point down here. Unless I'm rotating this point 180 degrees, which moves it down here, or 360 degrees, which leaves it right back where it started, this point that starts out at 0, 4 will not end up on the octagon. What that tells me is there's at most 2 angles that'll map this octagon to itself. Because to map the octagon to itself, all points have to get mapped onto itself. And by just looking at this one single point, I've been able to eliminate all angles except for 180 degrees and 360 degrees. My answer is certainly not 4 and it's certainly not 8. It's either 1 or 2. Because we're allowed to consider a 360 degree rotation, we kind of get 1 for free, right? If you rotate this thing 360 degrees, it's going to look exactly like it looks right now. That certainly works. But that's not the only solution. Because of the symmetry of this octagon, a 180 degree rotation will map it onto itself. We've already seen that works for this point that starts out at 0, 4 and ends up down at 0, -4. But that's also true for every other vertex. This point that starts out at -2, 2. If I rotated it 180 degrees, it would travel around a circle that looks very similar to this one in green, except the radius would be a little bit smaller, and end up down here at 2, -2. This point that starts out at -3, 0, rotated 180 degrees, would end up at +3, 0, and so on. Every vertex would map to the vertex directly opposite it, and because of the symmetry in this shape, all those points are on the octagon itself. And if all of the vertices map to another vertex, each of the lines connecting two vertices, so like this line segment right here that connects this point at 0, 4 to this point at -2, 2, would map to this line segment down here that connects -4 to the point 2, -2. The point that I'm trying to make is a 180 degree rotation and a 360 degree rotation will each map this figure onto itself. So the answer to this question is B. There are 2 different angles, strictly greater than 0 but less than or equal to 360 degrees, that map this specific figure onto itself. But again, as I said at the start of this video, you probably don't have to do that level of analysis where you're drawing circles and considering the radii of these various circles to come up with this answer. I bet a lot of people can just look at this shape and notice that if you rotate it 90 degrees, you're not going to end up with the same shape. But if you rotate it 180 degrees, you do end up with exactly the same shape. If you rotate it 270 degrees, again, you don't get the same shape, but back to 360 degrees, you do get the same shape. And then maybe you're like, right, but you only considered 4 angles, 90, 180, 270, and 360. What about a 45 degree angle? But a 45 degree rotation definitely can't work because if I rotated this shape 45 degrees, that would take this point to a point somewhere out here that would have to be the same distance from the origin as this point is. And the distance from the origin to 0, 4 is 4. But the distance from the origin to -2, 2 is not 4. It's the square root of 8, as you can figure out if you draw a right triangle and do a little a squared plus b squared equals c squared. Because we have an octagon, there's at most 8 different counterclockwise rotations that'll map this octagon onto itself. The 8 rotations corresponding with the 8 vertices. Every vertex has to map to another vertex. Hopefully that's fairly obvious. Rotate this thing like 10 degrees and you're going to have kind of a crooked octagon. It's certainly not going to map on top of the same octagon. So there's at most 8. However, just by looking at this point, we can eliminate 6 of those 8. The way we do that is we make the observation that the distance from this point to the origin is 4, and the only other vertex on this octagon that's a distance of 4 away from the origin is this one down here. So my only options for where this point end up are down here at the bottom or right back where it started. We have at most 2 solutions. Then just go through and double check that those 2 solutions work. Namely, if you leave everything alone, you're going to end up with the exact same octagon. And if you rotate everything 180 degrees, you're going to end up with the exact same octagon. We've shown 2 that work. We've shown that we can have at most 2. The answer is 2.